and welcome to this week's PYSQT seminar. Today we have Pablo Bermejo, which is working in San Sebastián. He's doing the PhD at the IPC, and he is also working as a researcher in multiverse. So today he's going to talk about QML for optimization via variational algorithms and coordinate transformations. Now you can start with your presentation. Thank you.
Okay, thanks a lot. Thanks a lot, Paul. Okay, let me.
Yeah, just share the screen. And if you have any questions, you can ask them in the chat, and I will ask this question to Pablo.
Okay.
Okay, so now just start, please.
Okay, thanks a lot. So first, I would like to thank you, Paula, and thank the organizers, because, I mean, as people said before, this is a really nice initiative, and I'm really happy to be part of it. So yeah, thanks a lot for letting me be here, okay? So as Paula said, I'm a PhD student at the IPC, okay, which is a research center in Donosti, okay, in Basque Country. It is over here in the picture, okay? It is quite a nice place, okay, to study and yeah, to hang around, okay. And I'm also working as a senior scientist at Multiverse Computing, okay, which is a company devoted to developing quantum and quantum-inspired solutions, okay, mainly based on tensor networks, okay, when I mean quantum-inspired, okay. So I'm also working on tensor networks myself, but in this case, I'll be focusing on quantum machine learning, okay? Quantum machine learning for optimization, okay, via variational algorithms and coordinate transformations. Probably here you will have a certain background in quantum physics, in quantum computing, okay? You will also find that this seminar, this talk will overlap a bit with previous seminars from, for example, Christian or Nadir, okay, from this series. But I think that it's quite okay to get the big picture of quantum computing nowadays again, okay? So for the people that is not really involved with this field, that have a certain background, okay, a quick one. So as you may know, this field of quantum computing started with Feynman's idea that, okay, if nature is quantum itself, okay, at the very small scales, we will probably need at some point quantum dynamics, quantum phenomena in order to describe it properly, okay, in the sense that classical devices at some point will not be enough to describe efficiently how nature behaves, okay? So from that point on, we have experienced like a huge progress in the field of quantum information in quantum computing, okay? First, this idea that quantum has to be used in order to describe quantum, okay? Then we find some theoretical progress on this field, okay, with the first quantum algorithms and the first architectures, quantum hardware devices, okay, in order to run these algorithms, okay, with the first hit in quantum computing, which is the construction of the first quantum computer based on nuclear magnetic resonance, okay, in 1998, okay. Then at the very first stage of 2 decades ago, we go through this whole era of quantum control, okay, in which we demonstrate that we can control quantum matter, okay. We can deal with light, we can deal with superconducting devices, trapped ions, okay, in a more or less efficient way, okay. And since then, we have been trying to scale these systems so that we can somehow make use of them in order to in order to run the quantum algorithms that were developed some time ago and that we are still working on, okay. In parallel, we tried different approaches in order to be able to use this quantum hardware already, okay, with no need to wait for the huge scaling thing. And in order to do that, we have tried what is called hybrid approaches, okay, mixing quantum and classical devices in order to take advantage of quantum dynamics, quantum phenomena, okay, to perform certain computations, okay. And I would say that since 3 or 4 years ago, we have entered in this race for quantum advantage, okay, proving that quantum can in fact overcome classical means in order to solve certain specific problems, okay? And in this highly non-linear path, okay, that quantum computing has been following, I would say that since probably 10 years ago or so, a field has erased, okay, and this is quantum machine learning, which can be included in the whole area of quantum computing. Okay, and we will see what this is, why it is important, and in fact, why we care about quantum machine learning, okay, because it is an area that it is catching my attention, okay? So basically, we are going through this NISQ era, okay, which stands for Noise Intermediate Scale Quantum Era. Okay, and this might sound discouraging, okay, because we don't like the word noise, we don't like the word intermediate, and it might sound like, okay, maybe there is still not too much to be done in this field, okay? In my opinion, this only means that there is a limited range of applications, okay, in order to be explored so far, because there are still strong constraints on the number of qubits to be used, the circuit depth of our quantum algorithms, okay, the connectivity between qubits. But for me, this only means that it is a challenging field, okay, but plausible and useful, because some people might give up on the idea of pushing this forward, okay, but in my opinion, it is only a matter of focusing on those areas, on those applications that are useful already, okay, and can have some impact in the near future, okay? And we think that one of these fields is quantum machine learning, okay? Quantum machine learning can be described as the intersection between a classical domain, a classical field study, okay, which is machine learning, data analysis, and so on, and quantum computing, okay? For those that are not familiar with these terms, it could mean that, okay, we might be employing machine learning techniques in order to better comprehend how quantum systems behave, okay, in the sense that we want to, I don't know, save data from quantum experiments or whatever. Okay, in this case, we are meaning just the opposite thing, okay, in the opposite direction. We are employing quantum systems, okay, quantum phenomena, in order to improve machine learning algorithms, okay? This is what my talk is about. And it can be, for example, to handle larger volumes of data, okay, more efficiently, to speed up training times, okay, or maybe to create new algorithms that cannot be developed by means of classical devices, okay, by classical software. So in this context, a question arises, right? In spite of physical limitations in NISQ devices, okay, we have noise, we are not still at the point of having reliable quantum hardware, okay, to deploy super huge or massive algorithms. But can we indeed start navigating research lines, okay, to overcome classical machine learning algorithms? That's probably the question in this field, right? For you to have some background, some idea, some intuition of what machine learning is, okay, in case you don't know anything about it, there are 3 main branches, okay? Supervised learning, unsupervised learning, and reinforcement learning, okay? Here you have some examples of the aforementioned, and yeah, they are basically nowadays restricted to classification, regression. In the case of unsupervised learning, generative modeling, okay, clustering, and reinforcement learning is basically decision making. So the question here is, can we use quantum, okay, quantum resources in order to push this forward? Well, what we see when we study the problems appearing in these fields, okay, is that they can basically be mapped to optimization problems, okay? They are optimization problems themselves, where you have a global minimum, okay, of a certain cost function encoding your target state, okay, the target state of your optimization process, And you are basically trying to know what that ground state is, okay, what that global minimum of your cost function is. Okay, this could be the correct labeling of pixels of a picture, okay, probability distributions, certain like distances between functions, whatever, okay? And yeah, as I was saying, the question here is, can we use quantum resources in order to improve our techniques to achieve such a minimum, okay, to achieve those solutions we are looking for in these fields? And as I was saying, since we are going through this NISQ era, we have to go for hybrid approaches, okay? Hybrid quantum algorithms, okay? Again, this does not mean that quantum cannot itself solve these types of problems, okay? In the sense that quantum has the potential to be useful enough to tackle these issues all on its own, okay? But the problem is that at the current state of development, okay, of quantum hardware, hybrid solutions are simply the best way to get the most out of our quantum systems, okay? Moreover, there are some other complications, such as the fact that we are still searching for the right subspace of solutions where quantum can be useful, okay, can be applied efficiently. Because nowadays, quantum is basically intended to perform computations that cannot be simulated classically in an efficient way, okay? And these hybrid approaches help integrate quantum in this NISQ area where we are still dealing with noise, we are still dealing with not super good quantum circuits, let's say, okay, because of the complications with our quantum hardware. Okay, so having this taste of the complications, the limitations of NISQ devices, but the picture also of machine learning. Okay, I would like to go a bit deeper into these fields to present one of the tools that is often employed in hybrid approaches, okay, to solve optimization problems. That was also introduced in Christian's talk, okay, which is variational quantum agent solver, okay. This is the technique that I have employed in order to get the results that I'll be showing in this talk. This is super used. It is very spread, okay, in the community, and it's probably the I would say the paradigm that will give results earlier, okay, in the field of NISQ quantum algorithms, okay. And the paradigm basically goes like this: the algorithm. So you have, for those of you that are not aware of it, you basically have a classical part, okay, represented by the orange color, and the quantum side, which is the blue one, okay. You will be basically interested in finding the ground state of a certain function, okay, again, encoding your optimization problem, okay. The ground state will give you the proper distribution of whatever you're looking for, okay. You have to design carefully and in a smart way your Hamiltonian, your cost function, so that the ground state gives you the proper pattern, the proper distribution, okay, the proper result to your optimization problem. And well, in order to do that, you will go through a two-step design, two-step algorithm. The classical side of your algorithm, okay, the one carried out by classical means, will dictate how the variational parameters should evolve in order to advance towards the ground state of your Hamiltonian or your cost function, okay? And in order to evaluate what your actual state is, you will use a quantum circuit, okay? This quantum circuit will basically depend on the variational parameters that have been tuned by classical means, okay? This is an iterative process, and the intention is that this process finds convergence at some point, okay? And you end up having the good ground state for your certain cost function, okay? This, of course, has certain advantages. You can, for example, explore a big space of solutions, okay, which cannot be simulated classically, okay, mainly when we have bigger quantum circuits, okay, we will be able to release algorithms which rely on certain, I don't know, for example, correlations between qubits that you can simply not simulate classically, okay? This quantum part also helps alleviate expensive calculations, okay, conducted with classical resources, okay, and good thing is that the VQE does not present many obstacles, let's say, in order to handle already useful algorithms, okay? Probably it has been difficult in the past, but I guess that according to the quantum hardware we are constructing nowadays, we can already build useful algorithms out of it, okay? But it has certainly certain disadvantages, okay? And those are very important ones. First of all, there is a complex trade-off between the answer expressibility of your quantum circuit, okay, and the way you convert to your optimum ground state, okay? Because of the fact that the Hilbert space that you are trying to explore is not as easy to explore as it seems to be, okay? You have to be careful with the way you design your quantum circuit and the correlations between qubits, okay? This also links with the following point, okay? It is difficult to target the right subspace of solutions you are looking for from the very beginning, okay? Sometimes the correlations inside your quantum circuit are treated as a black box, okay? You don't really know what you are getting out of it before you construct it, okay? Of course, you are trying to build this quantum circuit in reality, okay? So you are dealing with real quantum hardware, and you have problems derived from that as noises, okay? That induces convergence issues, okay? Here you have certain articles that talk about these problems, okay? There are some other, I would say, minor in the sense that they are specific, problem-specific issues, such as the fact that you cannot encode mixed states in your quantum circuit because that's exponential in time, and then you lose all the advantage of the quantum circuit, okay? And the fact that there are certain cost functions leading to overheading convergence, okay? This has also been proved in some articles, okay? The main point of these disadvantages is that they lead to two main issues, okay? Barren plateaus and local minima. And one of the articles I'll be talking about today at the very end deals with this issue, okay? Trying to improve grading methods via coordinate transformations, okay? In order to alleviate the effect of barren plateaus and local minima, okay? But before going to that part of the talk, I would like to quickly go through some of the things that we have been doing in the past, I would say last year and a half, okay? Trying to comprehend how quantum algorithms work, how we can deal with quantum circuits, with simulators, and so on, okay? And the first idea we came up with is this variational quantum and quantum-inspired clustering, okay? This is based on previous work from these two articles, quantum annealing for combinatorial clustering and the data re-uploading for a universal quantum classifier, okay? The main idea of the first one is that you can perform unsupervised machine learning, okay, unsupervised clustering. When we talk about clustering, sorry, it's almost always unsupervised, okay, in the sense that for those of you that are not familiar with this term, you have a data set and you are trying to group your points inside your data set into families, okay, based on some measurement, which can be distance, density, whatever, okay? In this case, as you can see, they are preparing a Hamiltonian, okay, for a quantum annealer, like the ones in D-Wave, okay, where you have a certain distance. I don't want to go into the details of the algorithms themselves, okay, but just for you to have a rough idea of what's going on, you have a certain distance, okay, between points. You have a variable in here, which is pointing out if a certain point belongs to a certain family, okay, where the points are I and j, and the family is are represented by this A letter, okay? And then just a constraint with a Lagrange multiplier saying that 1 point can only belong to one family, okay? From here, we took the idea of a distance-based clustering method, okay? We wanted to translate that into a quantum circuit, okay? And in order to do that, we took some ideas also from this data re-uploading paper, okay? This paper is cool, is really cool. It introduces two, for me, novel ideas. Maybe they were done before, I don't think so, which are the data re-uploading thing, which is the fact that you don't only take into account updated variables inside your quantum circuit, but you also introduce periodically the data you start with inside your quantum circuit, okay, by means of rotations. But in fact, I tried out that idea in my unsupervised clustering, okay, and it didn't work. However, I could take a different idea from that paper, which is the one related to non-orthogonal states, okay? The fact that you can encode more than 2 states per qubit, okay? So that you basically try to take advantage of the whole surface of the block sphere, okay? So that you can put, in this case, since we are dealing with a clustering, okay, can put more labels in a qubit than the 2 orthogonal ones, which could be 0 and 1, okay? This idea that might seem very difficult to implement has been implemented, okay, by the same group with certain experimental help, okay, in this paper. And since this was kind of viable, okay, in terms of quantum resources, we wanted to merge this idea of non-orthogonal states and unsupervised method, gate-based, okay, a gate-based clustering with these non-orthogonal states, okay. This is the whole idea of our article, okay. This is just for you to have again an intuition of how the cost function could look like. You again have distances describing the distributions inside your data set. With right now, we are looking at distances between each point and the centroid of the family each point belongs to, okay? And these F's in here are just fidelities, okay? Pointing out how far your points are from a certain label, okay? I don't want to mess with the algorithms, okay? Just for you to have a rough intuition that we are trying to cluster, we are trying to group points in a data set. We are doing it by means of encoding the labels to which each point could belong to in a single qubit, okay? And also important, we are using the same unitaries, okay, in our quantum circuit in order to distribute the points all along the block sphere, okay? The only differing point is the encoding one, okay? The one describing the position of each point inside your data set, okay? All the parameterized logical gates are the same for every single point, okay? So basically doing this, well, in case you want to have some references on the things that you can do with one qubit, okay, there's a good review done by the group of Alejandro, who was also here, okay, at ITHEMAT, for you to keep looking into this one qubit encoding one qubit algorithms, okay. But in terms of results, I was not probably expecting such a good convergence because of the whole non-orthogonal states that help compress the quantum circuit. Okay, but in fact, it worked pretty well. Okay, we ran the one qubit algorithm in a simulator and then also tried with a proper superconducting qubit. Okay, and we saw that, for example, in this case, we are trying to group points into families, okay, of a certain data set, in this case, Gaussian blobs, okay? We are using 3 non-orthogonal states in a single qubit, okay? And we are trying to distribute our points into the families they should belong to according to our cost function, okay, in terms of distances. We see that this is the right distribution, okay, the original one, and we can cut the good distribution, the good alignment or match between each point and its family. Okay, the fact that the colors do not belong to the good one relies on that we are using an unsupervised clustering. Okay, and we cannot determine what is the good family for each point if we don't bias the system. Okay, we don't want to bias the system, so we don't know if, for example, this yellow point is yellow or is black or whatever. We are just grouping points in terms of distances. Okay, we did the same for Gaussian blobs. Okay, and we went there a bit further. We tried with a well-known data set, which is the iris data set. Okay, and we saw that if you use this technique of using 3 labels per qubit, you can in fact classify the iris data set with a 96.7.7% accuracy. Okay, this means that out of 150 points, you miss 4 or 5. Okay, and those are the ones that you are missing, the yellow ones in here. Okay, that cannot be cut. Okay, with an unsupervised algorithm based on distances, because as you might notice, these yellow dots, okay, are closer to the blue ones than to the yellow ones, so they will simply be classified as the family below the other one. Okay, so I mean that's something you cannot really catch with an unsupervised clustering. You should go for semi-supervised or maybe supervised clustering with training data set and so on. Okay, and then we moved out of these non-orthogonal states, okay, and tried to implement the algorithm with more than 1 qubit. Okay, but in this case, we made use of the proper orthogonal states in the Hilbert dimension of the, in a Hilbert space of dimension 2 to the n. Okay, using in qubits, and we saw that again you can perform clustering, okay, properly enough. For example, here we have 6 Gaussian blobs. Okay, these are the original ones, and we are trying to catch the family they belong to. Okay, good thing is that right now we are not saying how many labels the algorithm should use. Okay, in the sense that if you are dealing with a Hilbert space of, I don't know, 2 to the 5, okay, you have now 32 orthogonal states, and I'm not saying that I restrict my algorithm to work on a subspace of that 32 dimension space. Okay, and good thing is that the algorithm is able to catch the proper number of labels itself. Okay, here it should catch 6 families. Okay, because those are the original ones, and using 8 qubits, you see that with no need to anticipate the number of labels, it clusters the whole data set with 100% efficiency. Okay, which is kind of cool. I mean, this is just like first results we had with our algorithm. Okay, and then just to sketch the idea, we thought that, okay, if this can be done for clustering, maybe we can move forward and use that for any kind of discrete optimization process. Okay, and just for you to have a rough idea very quickly, we try to find the ground state of this Hamiltonian. Okay, encoding more states per qubit. Okay, in this case 20 states in a single qubit. Okay, and we found that you can in fact find the ground state of this Hamiltonian with an error of 10 to the minus 6 using just 1 qubit. Okay, by means of this VQE with non-orthogonal states. Okay, so this is just a rough idea. And the question here is that, okay, if we were able to do that with a discretized system, okay, with discrete variables, can we move to the continuum? Can we use continuous variables, okay, using this kind of approach? And the question is that you, in fact, can do that, okay? And this is another result that we got in this field, okay? So again, the question is, we have a certain cost function, a certain Hamiltonian, okay, with continuous variables. Now we have a variable living in the real space, okay? We don't have 20 states per variable, it is just the continuum, okay? And the question is there a way to encode continuous variables inside qubit, okay, without going through the procedure of discretizing your domain and so on and so forth, okay? And in fact, you can, okay? You can encode continuous variables in a qubit at the expense of tomography, okay? This probably does not scale very well. We are thinking about certain approaches in order to speed it up, but yeah, it's just some proof of concept, okay? The idea is that you have a quantum state, okay? And each qubit, okay, will be described by a certain reduced density metrics, okay? And this reduced density metrics will basically be given by three variables, okay, which are defining your quantum state in a block sphere, which are the radius, this theta, psi or phi, or whatever you use, okay? So the idea would be basically map these variables inside your block sphere, okay, to the variables encoding the optimization problem, okay? And this will be given, again, by means of tomography, the fact that you can really read out these variables out of your quantum circuit, okay? The applications that this could have, basically continuous variable cost functions, as I was saying, and numerical analysis, okay? Based on interpolation, you can go for derivative, integration, and so on, okay? And we did that by means of expanding our solutions, okay? The solutions we are looking for, the ones encoding the ground state of our Hamiltonian or cost function into a certain series, okay? So that the goal of our optimization process would be finding the coefficients of our series, okay, such that you can minimize the distance. You can use whatever norm 2, norm 1 distances, okay? But the fact is that you have to go through this interpolation process by minimizing the coefficients and probably the frequency of the series you are expanding it, the run state solution, okay? One specific example is by means of Fourier series, okay? You have a certain cost function, you have an expansion in terms of Fourier series, you are trying to look for the proper C vector, okay, the amplitudes, the coefficients of your series, such as the whole series approximates the cost function you are looking for, okay? And we found that, in fact, it works pretty well, okay? We tried to interpolate some functions. We went there for derivatives and integration, and also some other kinds of problems, okay? For example, this is a simple function, okay? You go through, okay, maybe I missed the fact that since you can go for continuous variables, okay, in the coefficients, you have somehow to discretize your X space, okay? The points in which you calculate the distance between the function and the interpolation, okay? The coefficients are continuous, but the discretization in order to perform the norm-like distance is discrete, okay? I missed that. So we basically discretized the space in which we calculate this norm. We give continuous variables to the coefficients of our Fourier series, okay? And we try to perform this integration by means of an optimization process, okay? And we see that we can fit the function very well, okay, with an error that only explodes close to 0, because it is the relative error, okay, what we are calculating in here, and this is super close to 0 in terms of absolute values. This is very, very low, okay? We did that also for differential equations. We interpolate the original function we are looking for. We derivate the Fourier series already, okay? And we find a pretty good approach, a pretty good approximation to the solution of our differential equation. Okay, here it is the error of the differential equation. We did the same for integration. Okay, again, you see that it only explodes close to 0 because it is the relative error. Okay, and this is for coupled differential equations. Okay, this is not so good. I think that the error is around 10% for some intervals of your X domain. Okay, but still good enough. I also tried with PDs, but that's more difficult because in order to perform the interpolation, you have to somehow give an answer for your solution, and you have to be biased in order to know how the PD will look like. Okay, but still you can do it. I mean, I got some results, but they are not as good as these ones. Okay, and you can also go for other kinds of problems like continuous variable cost functions. Okay, I will describe rapidly what is appearing in here. You can, for example, say, okay, for example, in multiverse, right? We work with portfolio optimization, and we want to find what assets, okay, and how much of an asset we should include in a portfolio, okay? And in order to do that, we have to deal with a data set, okay, which is basically what my revenue per asset is or whatever, okay, and a coefficient for asset, okay, and in this case we are trying to reduce the variance between what assets I choose out of a data set, okay, and the average of each entry of my data set. Okay, this is for risk, it doesn't matter. The only thing important here is that we are trying to perform an optimization based on continuous variables. Okay, and the thing is that, for example, in here, what we are trying to do is minimizing the variance of a data set composed of 251 rows. Okay, this is your RT vector. Okay, then the RT with the symbol in here is just the average of each row. Okay, and we are trying to match each entry of each of my rows, okay, with a coefficient, which will be the same for each column of my data set. Okay, so basically it consists on optimizing this W vector, okay, for my whole data set. This constraint here only means that the coefficients are normalized to 1, and each coefficient can only be up to 0.1. Why this is important? Because these constraints are not so easy to implement with discretization systems, okay? For example, for this kind of approaches, for this kind of problems, D-wave is often used, okay? But in order to launch D-wave for these problems, you have to go for this discretization process. You are losing potential, you are losing capabilities because you have to waste quantum resources in the discretization step. Okay, and in fact, I saw that this kind of encoding, which is still a simulation, okay, of a quantum circuit, is lower than D-wave, which I guess that could be the best quantum solver so far for these problems. It's lower, but with higher precision, okay, with higher accuracy in terms of how much you approach the ground state of your cost function. Okay, which is kind of cool. And this was the quick review of the things I did in the past. And I will enter now in my latest release, okay? A paper that is submitted to arXiv 1 week ago or so that deals with improving gradient methods via coordinate transformations, okay? With certain applications to quantum machine learning. So, as I said in the very beginning, there are two main obstacles in machine learning, okay, which are Barron plateau and local minima. And these are even more important for quantum machine learning, okay? Those are caused because of vanishing gradients, okay? And this is mainly due to algorithm-related things such as you don't choose the good answer. It is very difficult to deal with the expressibility of your quantum circuit. Okay, it could be hardware related. It could be that your hardware simply has some intrinsic noise. Okay, but it will affect the way you move in your landscape of solutions, certainly, right? If you have a vanishing gradient, you will not be able to update your variables. Okay, and you will get stuck at some point, either in here, a variant plateau, or in here, a local minima. Okay, you want to reach this point, but because you have vanishing gradients, because of these things we have just commented, you will not be able to reach that ground state. Okay, there will be no further efficient optimization. Okay, and this is a very, very active area of research, at least in the quantum machine learning community. Okay, I encourage you to go through these reviews because they are really good. Okay, they really explain the whole problem and so on. And my approach to this problem, okay, in order to try to provide the community with something useful, right, was the idea that, okay, the problem in here, you can say it in here, is that we are getting stuck at dimensions. Okay, if you are trying to find the ground state of your f, moving along the x variable, okay, you are getting stuck at dimensions that are orthogonal to the cost. Okay, basically because you move along x, which can be considered to be orthogonal to your cost function, right? They don't belong to the same space, so to the same dimension. So my claim was, okay, let's include the dimension of the cost as one more coordinate to perform optimization over, right? In the sense that this dimension, the cost function, okay, will enter the optimization process as one more variable, okay, and we will deal with the cost both as a variable and as the cost itself, okay, creating like a self-consistent process. This sounds like pretty weird, but we will see pictures to clear it out, okay? And I basically went through two approaches in order to include this cost function in the optimization process. The first one using a change of coordinates, okay, going for hyperspherical coordinates. I will show why this is useful, and employing a variational reference frame, okay? This is what I mean by via coordinate transformations, okay? So the first one, with hyperspherical coordinates, okay, the idea is to perform the optimization, updating the gradient distance, okay, using the hyperspherical description, okay, but taking always the reference of your cost function in the original reference frame, okay? If you look at this picture, you see that, okay, you are stuck in here at this point P, okay, and when you try to perform your gradient distance, you cannot, basically, okay, you get stuck at it. So what if you move to this description with hyperspherical coordinates, okay, in which instead of moving along x, okay, you move along the radius and basically the hyperspherical coordinates describing your point, okay? In order to do that, you certainly have to use f of x to describe your point, okay? So that f of x will enter the optimization process as a variable itself, okay? And this is the whole description of the procedure. First, you have to perform the gradient in your new variables, okay? In the hyperspherical description, because in the Cartesian description, you get stuck at the variant plateau, okay? Doing that, you obtain a new point that you call P prime, okay? That will give you coordinates X prime, okay? Once you come back to the Cartesian description, okay? Giving you an update of your cost function, okay? You will not be able to move out of this point in Cartesian coordinates, but if you describe it with hyperspherical coordinates, since you are no longer in an orthogonal dimension to the cost, okay, you are moving, for example, along this direction, you will be able to change the value of your radius and your hyperspherical variables in order to generate a new f prime, okay, a new update version of this cost function. Good thing is that since you right now have a new updated version of your cost function, you will be able to generate the iterative procedure in order to update again the hyperspherical variables themselves, okay? So that you can generate an updated point, okay? And again in an iterative procedure, change your cost function, okay? Because you always have to have the reference in the Cartesian coordinates, because it is the description, you know how the cost function looks like, and perform the changes in the hyperspherical coordinates, okay? And this is an iterative procedure you perform over and over. Changes are done in here, okay, where you can move along directions that are not orthogonal to the cost, okay? In order to do that, you introduce the cost as a variable itself, okay, creating a self-consistent method, but the reference of the cost function, I mean, the value that you are trying to minimize, has to be always given in this description, okay? So it is a back and forth process, okay? And the other approach is, sorry, this is some benchmarks I performed, okay, just for you to, I want to go quick on this, we can discuss about it later. Those are articles that are well known in the community, okay, because they are explaining what the problems are with quantum machine learning and optimization processes, okay, and I would highlight this one, which is a problem in which the authors try to induce barren plateaus, okay, for a certain VQE, okay, and they see that with their method, okay, the change of from global cost functions to local cost functions, okay, they can get out of barren plateaus. I mean, I encourage you to read the whole paper and ask me if you are interested in this. They can get out of these barren plateaus with an average number of iterations of 29.14, okay? And we got the very same accuracy in terms of times you can get out of the barren plateau in just 4.7 iterations, okay? And those are also benchmarks for other articles, okay? I want to go quickly on this. The other idea is to employ a variational reference frame. Okay, again, you have a point in your landscape of solutions, okay? But you get stuck at a barren plateau, okay? An alternative would be to perform some kind of variation of your system, okay? Before it was the way you describe the point, okay? The coordinate system you employ to describe the point. And now it will be the variation of your reference frame, okay? You see that if you describe your point in this original reference frame, you have this barren plateau, you have this local minima, but if you kind of turn around your axis, okay, if you flip it somehow, you will see that in this description, okay, using again the cost function as a variable itself, you will not suffer from this barren plateau because along this axis, okay, that I call X rotated, this is no longer a barren plateau, okay? So you can really perform variations on this F rotated, okay? So that you can, when coming back to the original frame, have some updated version of the original cost function, okay? This is the whole description similar to the hyperspherical coordinates, okay? In order for you to have a taste of it, I chose to rotate just one variable of your landscape of solutions, okay? Variable I with respect to the cost, okay? And this is what I mean by that I employed the R2 rotation metrics, okay? It could be every single variable with respect to the cost, half of them, whatever, okay? And it is important to mention that this angle in here can also be optimized itself. Okay, and the idea is the same. You have this barren plateau in the original frame, you go to the rotated reference frame, you get a point described in the rotated variables, okay? You can move there, you can collapse the point in the original frame, okay? And you get an updated version of your cost function, okay? That way, you can again move to the rotated frame, okay? And update again your variables, taking into account that you always have to compare with the cost function expressed in your original reference frame, okay? And this is what I write in here. It is basically the same idea of the hyperspherical coordinates. It is very similar. If you get stuck with some description, try either to change the coordinate system, okay, or rotate the reference frame in which you describe the system, okay? And just to put some numbers on this, I performed also some benchmarks, okay? And you can see that, for example, for some other well-known articles, okay, proposing some good ideas to solve BQEs and so on, you can really achieve speed ups in either in the training time for supervised tasks, either in getting better ground states, okay, in terms of energy, but you sometimes get better results out of them, okay? Basically, I went through a lot of well-known articles, okay? I took the ideas and the implementations from Penny Lane's website, okay, Xanadu's website. They posted their, I don't know, many algorithms extracted from well-known articles, okay? And I saw that for the case of the variational reference frame, for example, which is something curious, out of 20 algorithms that I tried, I improved something like 15 or 16 of them, okay? Again, when I say improvement, I mean better convergence, okay, in terms of a number of iterations of steps to achieve certain value of your cost, for example, or a lower cost function, okay? This is somehow big in the sense of many examples to be explained and so on, but since it's already kind of 50 minutes, right? I guess that it's time to stop. So in case you want to comment something about it or get deeper into the solutions and so on, just let me know. I'll be happy to share it with you and to talk with you. Okay.
Thank you, Pablo. It was a very nice talk, and for me, the results were like very impressive. So now it's time for questions. So if you have any questions, you can like write it on the chat, or maybe we can like unmute you so you can ask them yourself. In the meantime, I would like to do like some questions myself, since there are no questions right now, so people can start thinking. The first question would be, so I found this last part very interesting because it's something very intuitive, and I would like to know if there are like, it is something heuristic, or do you have any intuition, mathematical intuition that says, okay, this is going to work like in this case or whatever?
Yeah, probably, I mean, taking into account the results that I got, there are probably some limitations. For example, in the case of hyperspherical coordinates, okay, when you move to this description, you see that you don't get good results or better results that often, okay? And I think that probably the landscapes we are dealing with are so bumpy, okay? They have so many local minima and so on, that at some point, it doesn't really matter if you use the Cartesian description or the hyperspherical description, because you will often encounter local minima and barren plateaus in every single
both
direction.
Coordinates,
Yeah.
Okay, so
that's the good thing. Yeah, that's the tricky thing. But that's the good thing about the rotational frame, because with the rotational frame, you can certainly just move a bit, okay, in the sense that you get stuck at some point and you perform an optimization over theta, the angle you are rotating around, and you often see improvements in the sense that maybe that's probably more efficient in the sense that you can navigate the bumpy landscape with a better approach, I guess, because of this whole landscape of local minima, barren plateaus, and so on. This gives you a degree of freedom that you don't have with the hyperspherical coordinates, because there you don't have this theta to optimize around. So yeah, that's probably one important thing. And yeah, about the heuristic part, since I found better solutions for, I would say, 85% or 90% of them, I think that it should work for most of the VQs that we are currently seeing, I guess. Yeah, I mean, as a picture, it makes sense to me that it works. If the machine is doing what I think it's doing, I think it is not heuristic. I think it makes sense.
Okay,
because the tricky thing is how it understands that you want the cost to be cost and variable.
Yes, that was the most different things. Yeah.
Yeah. So probably the self-consistency there can fail, and you mess the whole algorithm up, and you screw things up, and you don't get the right solution. But yeah, I guess for the variational coordinates, it is more promising, I guess. Yeah.
Mm-hmm. So, okay. Do you have any questions or something that you would like to comment? Okay, so I think I'm going to do like one last question because it's almost time. It's like a more general one because I myself also work in this in similar like themes. I'm very interested in this QML application also to numerical analysis that you've commented, and I know that one of the main limitations in this in classical machine learning or numerical analysis is the problem that we have with the dimensions. So we have a lot of variables. We cannot deal with that in a computer. And I would like to know, how do you plan to deal with that with your approaches, like with the quantum ones, and take into account the limitation of the NISQ devices?
The number of variables, you mean
You mean
you
like,
have to encode in your quantum circuit?
yeah, or the number of points you have in a grid if you try to represent a function? Like,
Yeah,
so how
that
many
is,
variables do you have in quantum machine learning, which is also problematic if you have a lot of them?
yeah, that is something I'm currently looking into too. But I don't have yet an answer to that, because whenever I have something I cannot deal with for optimization processes, right now I am switching to tensor networks just to have like, I don't know, a first intuition of what's going on. But it's true that, I mean, whenever it is necessary to move for higher or bigger correlations in terms of range, yeah, that's an obstacle. I'm also encountering, and I don't have an answer to, obviously.
So you just, but it's interesting because you can use your methods or adapt them to tensor networks to try to reach that. Like
I tried to implement the variational coordinate for MPS. I failed. I mean, I'm still doing it because I guess that in order to do that, you will have to come up with some get that is not so easy to come up with because because yeah, basically in your tensor network, if you try to introduce a change of coordinate, you have to do it by means of linear methods, for example. So I mean, of some kind of approximation and so on. So for the hyperspherical coordinates, it could be super slow, I think, because you have to approximate the nonlinear transformations all the time in every single iteration. And probably for the variational frame, there's something more to be said, but I mean, it is still work in progress. Yeah, but it's a good question.
It's good to know. Yeah. So I think we are done, and well, thank you so much for your talk. It was very interesting. Well, last, I would like to say that you are welcome to submit your own proposals if you want to participate in these seminars. Well, see you soon next month.